Hey everyone. So we just wrapped up today's class, and one of the things that we were talking about in class today was taking a look at the Gravitron problem. It's in your circular motion packet, page number 6, problem number 10. It's the one where Darren's inside of a Gravitron, where there's there's rides that you get on where it spins really fast and you're like sucked to the wall. And it's a classic physics problem. So I gave you guys a chance to kind of talk it out. It gave me a chance to hear what you guys were thinking about that problem. And like I said, we start to look at how the normal force for us, is starting to change its direction a little bit because we're moving differently. Normally, the normal is just straight up or perpendicular to a surface if we're on like an inclined plane. But now we're starting to see how that normal force is changing a little. And I just wanted to walk you through that problem real quick. So it is problem number 10. I'm just going to show it here on the screen. Just a second to figure out where I am up here. Here we go. So it's that problem right there. Darien is in a barrel ride on the amusement park. And so this is Darien here. And what I want to do is I just want to label the forces real quick on Darien. Okay, so here's Darien. He is on Earth, so he's going to have weight. And this ride spins around real quick and the floor drops out. He doesn't fall down, not because, right? Because if there's a surface that he's standing on, he would have normal up. The surface drops away from him. And then what allows him to stay put is this friction. And it is static because he's not moving up or down. But he is moving around a circle, therefore he's accelerating. His back is pushed up against this wall. He feels like he's being stuck to the wall because there is this normal force. This normal force is the agent for centripetal force. It's the thing that's causing him to move in a circle. He wants to go straight. So if this ride is spinning this way, he wants to keep on going straight, but he can't. He literally is running into the wall because the wall is spinning around him or curving in front of him, and he wants to go straight, but he can't because he's running into the wall. You don't feel like you're running into the wall. No different than when you're in a car and you make a hard turn and, back in the day, we didn't have seatbelts and we would slide all over the car. You'd feel like you're being pushed against the wall of the car. You're not being pushed against the wall of the car. You want to keep going in the direction you were already going. It's Newton's first law. You want to keep going straight. In that barrel ride or Gravitron ride, you want to go straight, tangent to the curve. But you can't because there's literally a wall, a curve. If you're in a car, it's the door. Like whatever it is that's in front of your path is causing you or forcing you to turn. In this case here, he is stuck to the wall. The force of him being pushed against that wall is what we would feel. He's traveling and the wall pushes against him, causing him to turn a little. And it's a continuous push towards the center of a circle. You get a centripetal acceleration because you have a centripetal force. So he's accelerating towards the center of a circle because of this normal force that he's experiencing due to the wall. And when we take a look at the answer to the sticking of the wall phenomenon, it's his natural tendency to move tangent to a circle, but the wall pushes him inward. And then when we do this free body diagram, obviously we can talk about F net equaling MA, and we're dealing with a circle, so it's MAC. And we can sum up all the forces in the X, and that's the normal. And we can sum up all the forces in the Y, and we get friction minus weight. We're not accelerating in the Y plane, so our mg is equal to mu times the normal. And then MAC is equal to normal. We can solve out for this normal. So mv squared over r and if we wanted to, right, we could get the centripetal acceleration, solve for the normal force. We can figure out the mu. You can just derive an equation in terms of normal force. You can derive an equation for mu. You can do a lot of things here from that point if we have more information about Darien. The idea is that we're doing nothing different than we've been doing in forces with this stuff over here. Drawing free body diagrams is no different than what we did in forces. You just need to recognize that in a circle, when you're moving in a circle, you're accelerating because you're moving towards the center of a circle. Your direction of your velocity vector is changing. You have a constant speed, but a continuous change in direction, which is acceleration. And when you're identifying the agent for centripetal force, it's the force pushing you into the center of a circle or causing you to turn and make that circular path. And then the last thing on this problem, remember that you want to keep going straight. An unbalanced force is going to cause you to change your motion. That normal is not balanced by anything. You're going to change your motion. All right, I think I said enough about problem number 10. You guys did great today in class. Hope you had a little bit of fun, and I'll see you next time.